So in the previous lecture, we solved a system of linear differential equations involving an initial value problem. That is, we were given a vector here in order to solve, to find a particular solution to the system, unlike the other one we did prior to that one. And we got this particular solution. Well, if you would like to visualize the solutions to these systems of differential equations, well, number one, you could rewrite the solution to the system from vector form to parametric equation system form. That is, you have an equation for x and for y where x, that is 1 times the exponential times 2, that is 2 e to the 4 t, plus 2 times e to the negative t times negative 1, that makes it a negative 2 e to the negative t. And then the second equation becomes e to the 4t times 1 times 3, that's 3 e to the 4t, plus 2 times 1, which is 2 e to the negative t. So that'll be the solution in parametric form, which is, I mean, it's a more convenient form if we were to look at the graph of the solution. And you guys know how to graph this in Calc 2, and you use this a lot in Calc 3. So you can simply go to your graphing calculator, and I already pre-typed the equation, so I don't waste too much time on that. And let me show you the graph, okay? The graph of the first one should look, okay, it's gonna take a few seconds. Also recall that what you call for parametric equations, direction matters. How does it go from left to right? That's indicated with an arrow because in the end, well, eigenvalues and eigenvectors here actually those are vectors that have some direction. Okay, so that's one way to relate this. Okay, let's do the next example. That is for the next case. What if we have in value. So we sort of have a situation here because if for whatever reason, for a 2 by 2 matrix, we only get one eigenvalue, well, we would expect to get two instead, don't we? So because we want to obtain two solutions that comprise a fundamental set, a linearly independent fundamental set of solutions. But since there's no second eigenvalue to get that corresponding eigenvector and consequently get that second solution, what do we do? Okay, so listen up. Suppose lambda 1 is an eigenvalue of multiplicity 2, okay? And that there is only one eigenvector, unfortunately, associated with this value. So a trick to get the second solution, because again, you want to get x equals to x1 plus x2. That's a sum of two solutions, don't we? Okay. To get a second solution, x2, we're going to write this vector here. K times t e to the lambda 1 t plus p e to the lambda t. Remember the repeated roots for the, the higher order differential equations in which depending on the multiplicity of the root to the auxiliary equation, we multiply by powers of t. Well, do you see this multiplication by a power of t? Well, it's back but in the sense of matrices here. Now, what about this vector p? How do we figure out vector p? So here's what we do. We're going to set a second eigenvector equation. So, you get the eigenvalue, do the eigenvector, boom, you're done. Okay? But to get the second eigenvector, instead of setting it equal to 0 like we did with the first eigenvalue, we use the vector k. We set it equal to the vector k we found in the previous part. Well, how about we see this in action so it makes more sense rather than this symbolic definition. Okay, so we have this system right here. How about set it like in matrix form, okay? That is, oh, come on, equals to -6, 5, -5, 4 times xy. where in this case A, okay, our matrix A, um, it's this coefficient matrix, and well, we need to find the determinant of A minus lambda I, and let that be equal to zero, not a zero vector, because the determinant equals a scalar, not a vector. All right. So what else do we do? Okay, so subtract lambda from the elements along the main diagonal, and at once I'm going to set the determinant. I'm going to set the determinant notation. So that's 4 minus lambda 5 and negative 5. Let that be equal to 0. And I mean, evaluate the determinant. Negative 6 minus lambda times 4 minus lambda time, or rather minus 5 times negative 5, which is 25 negative. So 25, but actually becomes positive because of negative times a negative equals positive. Okay, set that equal to 0. And let me do 6 times negative 4, that's a negative 24. Okay, negative 6 times a negative lambda, that's plus 6 lambda. All right, wait, that's plus 6 lambda. And then negative 6 times 4, that's a no, I already did that, minus 4 lambda. And plus lambda squared plus 25 equals to 0. Simplifying our terms in here, what do we get? 25 minus, okay, let me do the square one. Lambda squared plus 2 lambda, and then plus 1 equals to 0. Factors of 1 that add up to 2 have about 1 and 1. Did you see how we have a repeated eigenvalue, a repeated root? Lambda plus 1, lambda plus 1 equals 0. So in this case, our eigenvalue equals to 1. And it happens to be repeated. Okay, it happens to be repeated. All right, what do we do next? Okay, we'll get the corresponding eigenvector. Okay, so for this, uh, so let's set for lambda equals to 1, that equals a minus I, essentially, times k, the vector, the eigenvector, equals the 0 vector. Yes. Which one? Oh, yes, it's yeah, it's negative. Yeah, right? Negative 1. Yeah, for negative, and that actually becomes plus, right? Right here. Thank you, thank you. Good catch. All right. So, what else? So this would be essentially negative 6 plus 1, 4 plus 1, and the remaining elements remain the same. And actually, I'm going to do, okay, now this is not a determinant. This is going to be an augmented matrix. And this becomes negative 6 plus 1 is that negative 5, 5, 0, and negative 5, 4 plus 1, another 5, and then another 0. Come on, these two rows are exactly the same, right? So we're going to get infinitely many solutions for this system. So in this case, how about we just grab any of the rows and turn it into an equation, decode it into an equation. That is negative 5k1 plus 5 k2 equals to 0. And I'm going to solve for k1 right here. So 5k1, or rather negative 5k1 equals to negative 5k2. So k1 equals to k2, right? And here is where we give k2, or I rather, yeah, k2 any value. Whatever value you want to give, however, give the simplest value possible. So let k2 equals to 1. That means k1 equals to 1. So the corresponding eigenvector k equals to, what is that? 1, 1, right? But guys, that's only half of the solution to the problem, because this is we are expected to get two solutions, one for x and one for y technically. So how do we get the second solution? So here is what we're going to do. So to find p, so we need the second vector. To find p for the second solution, p is a vector, by the way. Set a minus I minus lambda I times P, okay? And let that be equal to the vector K. We know A, we know lambda I, we know K, so we just set this equal to P. All right, guys, just so it doesn't look weird, let me do the whole thing here. All right, so number one, essentially, well, we already have A minus lambda I, all right? That is A minus lambda I, which is A plus i's essentially. That's a negative 5, 5. Another negative 5, 5. Let that be equal to P1. I mean, times P1, P2. That's the vector for the eigenvector we're looking. All right. So, and in this case, let this be equal to K1, K2. All right. Let's just substitute the K1. Okay. So let me do negative 5, 5, negative 5, 5. I'm going to, okay, I'm going to omit the P1, P2 because, well, that's going to be the eigenvector, and I'm just going to go the the augmented matrix form, which is negative 5, 5, negative 5, 5. And that, what's our vector? 1, 1. Okay, guys. Again, don't even bother reducing the matrix. Isn't it easy to see that the two rows are exactly equal or maybe a multiple of each other? So just grab any of the equations and decode it. I mean, any of the rows and decode it into an equation. That is, I'm going to take the second row or the first one. Doesn't matter. They're the same. Okay, so that means negative 5, not k, actually p1 plus 5 P2 equals to 1. Okay? All right, well, in this case, what do we do? Okay, I'm going to solve for P2 in this case because that's the one that already has the positive sign. You can solve for the other one if you want. Okay? Now, 5 P2 equals to 1 plus 5 P1. And then divide both sides by 5 to get P2 equals to 1 plus 5 P1 over 5. Do not split the fraction. Okay, guys, when it comes to a situation like this, it gets a little weird because, especially because of the number we would give to P1 this time, which again, you can give it your favorite number. It doesn't matter, 1, 7, 5 itself if you want, whatever number. But in this case, I'm going to give P1 the value of 0. How about that? I'm going to let P2, oh no, no, P1 equals to 0, and that is P2 equals to 1 plus 5 times 0 over 5, and that's going to be P2 equals to 1/5. Okay, in this case, I know this is one of the components of the vector ended up being a fraction. I mean, you could maybe figure out a value for P1 such that maybe no, I don't think there's a way to find to multiply a number by 5, add 1 and divide by 5 and get an integer, right? I don't think so. Yeah, so in this case, we'll have to leave it like this. So P, that's uppercase P by the way, that is 0, 1/5, okay? And x2, which is a t e to the negative t in this case plus p e to the negative t. That's the same eigenvalue, which is the coefficient of t. And in particular, x2 equals to k. What's a vector k? Wasn't that 1, 1? Yes, 1, 1, 1, 1, t e to the negative t plus p. What was p? 0, 1/5 e to the negative t. Okay. Well, that's only the second solution. Now let's write the general solution. Okay. General solution. That'll be x, which is x1 plus x2, a linear combination of the two. So that is x equals c1 e to the negative t times the eigenvector 1, 1 plus c2 times, well, actually, I should have done c1, c2 here, right? Technically. And that is all this madness I had here. 1, 1 t e to the negative t plus 0, 1/5 e to the negative t. So this is the trickiest case, guys. Whenever you have a repeated eigenvalue, you have to set up and you have to set a second eigenvector equation, but instead of setting it equal to the zero vector, you set it equal to the eigenvector you found for the unique eigenvalue you obtained. All right. And yeah, this is how this looks like. Don't bother distributing. That's fine. This is good enough. No problem. All right. All right. Case number 3. And don't let this scare you. Yes, this one, guys, it's more bark than bite. That's all I would like to say about it. I'm going to give you a big formula for the case for complex eigenvalues. So, well, guys, what happens when the eigenvalues are complex? The eigenvectors are also complex. What did we find out about complex eigenvalues? That they are conjugate pairs. What did we find about the corresponding eigenvectors? Likewise, they are complex conjugate. Didn't we do that in the previous section? Okay. Now, let me give you this formula right here. So the solution would be x equals c1 e to the alpha t b1 cosine beta t minus b2 sine beta t plus c2 e to the alpha t times b2 cosine beta t plus b1 sine beta t. Wait. There's a lot of symbols here. What's alpha? What's beta? Alpha, it's the real part of the complex eigenvalue, while beta is the imaginary part of the complex eigenvalue. What is this beta 1 and beta 2? Okay, guys, the eigenvector we obtain, which will be another complex eigenvalue, we will split that eigenvector into a real vector plus I times another vector, which is a real vector and an imaginary vector. So those are going to be our B1 and B2. And well, uh, what is the proof of this what's the proof for this formula? Well, I don't want to write the whole thing. I'm going to explain it as a matter of a presentation instead. Okay, guys. So let's suppose you get a solution of the form. I mean, isn't this like the form of the solution to C1 K1 e to the lambda 1 plus C2 K2 e to the lambda 2 times C? I mean, it's exactly the same. Okay, it's exactly the same type of solution, except that this time we will replace lambda with, guess what, alpha b sub 1. Okay, and that's going to be alpha plus beta I, alpha minus beta I. All right, so that's what I'm doing here. And well, what happens next? Let's denote case of 1. Okay, that's the eigenvector to be b1 plus ib2. In case of 2, b sub 1 plus ib2. So the eigenvector, which happens to be complex, I'm going to split it into two parts. And imagine a real part plus plus minus its imaginary part. Okay, so right here I will replace then k1 b1 plus ib2 with b1 plus ib2. And the second eigenvector, I'm going to replace it here. Okay. So that's k1 and k2. All right. Okay, the rest of the problem, guys, is a few algebraic steps. Okay, so no, not all, not a few algebraic steps. Actually, right here, what am I doing? E to the alpha plus beta I. This is an exponential raised to a sum of terms. That is e to the alpha times e to the beta I. Do you guys agree with this by laws of exponents? So I'm keeping the imaginary after the group of parentheses and the real before the group of parentheses. Are you guys following me here? Okay. So I'm going to use Euler's identity to express e to the imaginary ones, all right? You're using cosine theta plus I sine theta, and e to the negative I theta equals to cosine theta minus I sine theta. That's going to make our job a lot easier. Let me use other highlighters here. How about purple for e to the I? That becomes this one. And how about a green? This one right here gets replaced here. All right? Just a substitution. That's all it is. Okay, guys. What happened here? Looks like I just copied the same line, right? I didn't do anything interesting here. Anyway, so guys, the rest of the problem, can you think about doing a lot of foiling here in this first term, and then another foiling here, a bunch of terms, isn't it? Okay, after doing a lot of algebra here, that's going to take us to, well, actually, to all this madness here. All right. Okay, guys. When we're doing this algebraic process, we're going to get a bunch of real terms and a bunch of imaginary terms. What I'm going to do here is group the imaginary terms with the real terms with the real terms and the imaginary terms with the imaginary terms. All right. So how do we go about that? Well, notice in this case, these guys right here are all reals, right? These are all reals. And right here, okay, I could factor the imaginary unit I. That'll be I times C1 minus C2 e to the alpha, blah, 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 right? That'll be the imaginary term, okay? So let me use a different color for highlighting all this. Okay, imaginary one. Okay, guys, what do we know about a constant plus or minus a constant, even if it's imaginary one? Isn't that just another constant? Okay. And in this case, check this out. I'm just setting C1 plus C2 equals to a D1 right here. And IC1 minus IC2 equals another constant, another arbitrary constant, D2. Okay. And that's what they become. Let me use different highlighters to highlight this. D1, C1 plus C2 becomes D1 and D2, which is IC1 minus IC2 becomes C2. But guys, can't we use any letter for arbitrary constants? How about we just use C1 or C2? I mean, because it's just an arbitrary constant, and this is the derivation of the formula right here. All right, which is going to be very convenient. Now, derivation looks scary. Yeah, I agree. There's a lot of algebraic steps that I decided to just show as a presentation rather than doing the whole thing. But there's a great advantage when we are working with complex eigenvalues. And that advantage is that we only have to worry about one eigenvalue. That's it. Find the complex eigenvalue, worry about one, find the corresponding eigenvector, because, hey, look at the definition. All we need is lambda 1, because all we need to know is what's the real part, what's the imaginary part, and because of the signs by absorption, they just go away. That's it. All right. So let's have a look at one example. So we have the following system where, in this case, x prime y prime equals to 6, -1, 5, 4. That's x, y. All right. All right, well, let's get the eigenvalues. So that is, let's find the determinant of a minus lambda I, and let that be equal to 0. That is 6 minus lambda, 4 minus lambda, negative 1 right here, 5 right there. Let that be equal to 0. Okay. So that means, okay, 6 minus lambda, 4 minus lambda, minus a negative, which is plus 5. Let that be equal to 0. Let me continue up here, okay? Let me continue up here. That is 6 times 4, which is 24. 6 times negative lambda minus 6 lambda. Negative 4 times lambda, that's minus 4 lambda. And positive lambda squared plus 5. All right? Okay. So lambda squared equals to, no, lambda squared minus 10 lambda. And 24 plus 5, is that equal to 29? And let that be equal to 0. Okay, let me make this look like a 10. Perfect. Well, factors of 29 that are negative 10. Good luck. Well, quadratic formula. Minus negative 10, that's a plus 10. 10 plus or minus the square root of negative 10 squared plus 4 times 1 times 29. Everything divided by, what is that? 2 times 1, right? And well, this reduces to 10 plus, oh yeah, 10 plus or minus the square root. Okay, negative square, that's 100. 4 times 29, is that, I believe, 1, 116, I believe it is. Yeah, 116, I believe, oh yeah. So that reduces to negative 16 inside of the radical. And then divide by 2. Well, 10 is still 10. Lambda equals to 10 plus or minus the square root of negative 16. What is that? 4i, right? Be careful. Imaginary units and everything divided by 2. Okay, lucky for case, both numbers in the numerator are evenly divisible by 2. So this would be 5 plus or minus 2i, right? So let's go ahead and find the corresponding eigenvector. So eigenvector for lambda equals to, and I'm going to do the positive. You can do the negative, guys, if you want. It doesn't matter. But I'm going to do the positive. 5 plus 2i. Okay. And let's see. That is a minus lambda I times k equals to 0 vector. Okay. So that is matrix A, which is, what is that? 6, right? Minus lambda, be careful, minus parentheses 5 plus 2i. The second and the next element becomes a negative 1, right? And then 5 remains 5, and then this would be, let me do negative 1 here. That is 4 minus 5 plus 2i. And well, actually, let me do the augmented matrix, okay? Let me do the augmented matrix, and well, let me simplify. Let's try to work our system of equations here. Okay, so 6 minus 5, is that equal to 1 minus 2i? And then negative 1. And then 5 remains 5. 4 minus 5, is that negative 1 minus 2i? And let that be equal to the 0 vector. All right? Okay. So guys, again, what did we say about complex eigenvalues? Don't even bother. Don't even bother reducing the system. Just grab your favorite row. I'm going to grab the first row. Let me highlight the first row and turn that into an equation. 1 plus 2i times k1 minus k2 equals to 0. And in this case, You don't want to solve for k1 because you will have to divide by a complex number. You don't want to divide by a complex number. It's doable, but it's not efficient. It's not worth it. Okay, so I'm going to solve for k2 here. So k2 equals 1 plus 2i k1. In this case, we will let k1 equals to 1, okay, because it works. That is, k2 equals to 1 plus 2i times 1, and k2 equals, 1 plus 2i. Okay, what's the eigenvector? So k will be equal to, okay, k1, wasn't that a 1? Okay, k1 is 1. What about k2? 1 plus 2i. So that is an eigenvector. All right? Yes. Which part? Over. Oh, wait. What, oh, no, no, you're right. You're right. Right. Thank you. Thank you. So this is supposed to be minus, minus, right? And that's a minus, and that's also minus right here. Thank you. Good catch. And okay, you're right. Thank you. Thank you. Yeah, I don't know what happened. Oh, guys, so that's K. Okay. Again, don't bother finding the eigenvector for what is that? For 5 minus 2i, because we already have one of the eigenvectors that can be split into a real and an imaginary one. That is, okay, let k, which is our vector 1, 1 minus 2i, okay? So, do you guys agree that this would be the vector 1, 1 plus I times 0, 2? Do you guys agree with this? That is 1 plus 0i, isn't that equal to 1? And then 1 plus 2 times I, that's 1. Oh, no, not mine. That's well, no, that's plus. Okay, that's plus right here, but let me put a negative in the component of the vector. Okay, let me put that negative there. Okay, so keep the negative in the vector, not in the. Okay, what this with b1 equals the real vector, the real part of this vector k, which is 1, 1, and b2, which is the imaginary part of the eigenvector. And guys, we're pretty much done with the problem. All we need to do is go back and substitute into the big formula. All right? That's it. You see how these systems, despite they could be a little scary at first, they're not as bad, and they're not as bad as they look. So x, that means x, what is that? X equals to, so C, okay, let me write the big formula first. C1 e to the alpha t b1 cosine beta t minus b2 sine beta t, close the brackets, plus second solution, C2 e to the alpha t b2, careful, b2 cosine bt minus, no, that's a plus b1 sine bt. Okay? What's alpha? What's beta? Well, alpha and beta are the real and part of the complex eigenvalue, respectively, right? So, alpha, what was that? Wasn't that alpha equals 5, beta 2? Alpha equals 5, beta equals to 2. I'm not going to write B1 and B2. You have them at the top, all right? So, simply go like this. The solution set would be C1 e to the 5 t. What's B1? 1, 1 cosine of bt. What is bt? What is, I mean, beta t? That's 2t plus no, rather minus b2, which is 0, negative 2, and sine 2t, okay? Plus c2 e to the 5 t, b2, which is 0, negative 2, cosine 2t plus 1, 1, right? Let me keep going. Need more space. Okay. 1 times sine 2t. And that is the solution to the system. And you may want to distribute if you want, so that's fine. Okay. However, well, actually, I'm going to do it for this case because I would like to show you the graph of this of a system having complex eigenvalues. Okay, let me go x and y equals, okay, let me multiply C1 exponential times 1 times cosine times 0 times m. That'll give me C1 e to the 5t cosine 2t. Here I'm going to get a 0. I'm not going to get anything. Plus C2 times 0 times cosine. I'm going to get 0 here. But in this case, C2 e to the 5t times 1 times sine 2t. That'll be plus C2 e to the 5t sine 2t. So that's the first component, right? And what about the y equals to, okay, the y equation. So in this case, I'm going to multiply C1 e to the 5t, and I'm going to go 1 times cosine 2t, that's a cosine 2t, minus minus, isn't that really a plus? 2 sine 2t, okay? And for the second term, plus C2, C2 e to the 5t times the negative 2, that's actually, well, let me do C2 e to the 5t, and let me factor the exponential, that'll be negative 2 cosine 2t plus 1 times sine 2t, which is plus sine 2t. And that is the solution. That's the general solution. Okay, guys. Well, how can we graph this if we don't know what C1 and C2 are? Well, technically here we would need to have an initial condition, say x of 0 equals to 0, 0 or any vector. But in this case, let C1 and C2 equals to 1, just for the sake of simplicity. I'm just making up some arbitrary constant so I can graph this. What does the graph of this look like? Well, okay, unlike the this graph, which is actually a combination of exponentials with positive and negative exponents, that actually resembles like the graph of a hyperbolic function, isn't it? A little bit shifted to the left, and But what about this? The result of something like this. Okay, I mean that's gonna take a few seconds before it graphs something. Yeah, okay. It will look like a spiral actually. Yeah, that you can, yeah, if I zoom in, it's going to keep like going into, and then it's just gonna go like out. Okay, guys, why am I doing this? Why am I showing you how the graphs look like? Because on the homework, you'll be doing this sort of thing in the next section, in the applications, in the modeling. You will be asked to choose the graph that best represents the solution. So you will solve an initial value problem, put it in your calculator, and choose the graph that best fits. So that's what you're going to do. All right. And I believe this is the end of the section, isn't it? Okay.